Okay, last time we started 2.5 transformations of functions, but we didn't finish it. We talked about uh, shift of graphs. You know, uh, you can shift the graph of function uh, up or down or left or right and get another function. And then we talk about the reflecting graphs. You can reflect the graph of a function or relation through x or y axis to get another relation. Okay, so we did one example of reflecting graphs. Let's just continue and do another one. So in this example, we need to compare the graph of each function with the graph of f equal to square root of x minus 1. Okay, so this time we are given the functions f, and then we are given g and h, and we need to tell what's the difference or what's the relation between the graphs of those functions. Instead, we join the graphs. Okay. So we're given function f equals square root of x minus 1, and uh, in part A, we have not function g equals negative square root of x minus 1. Okay. So you can see you just put the negative to the whole function. So in other words, g is just negative f, right? So in that case, if you remember the rule, the graph of f and the g will be symmetric with respect to the what? X-axis, right? Because you change y to negative y, okay? Or the graph of g is a reflection f in the x-axis, all right? Now in the part B, the function h is square root of negative x minus 1. So in this case, we change the sign of x into negative x from f to h. And in that case, you reflect the graph of f across or in y-axis. When you change x to negative x, if you think about it, you are reflecting across the y-axis. So the graph of h equal to square root of negative x minus 1 is a reflection of y in the y-axis. So you can double check the graphs of those three functions, and you can see that's indeed the case. On the left, we have the graph of f equal to square root of x minus 1 in the first quadrant. In the second graph, the graph g is negative square root of x minus 1. It's in the fourth quadrant, and you can clearly see that it's just the reflection of f across the x-axis or in the x-axis. And in the right, on the right, we got the graph of h equal to square root of negative x minus 1. As we just said, it is the reflection of the graph of f across the y-axis or in the y-axis. You can see that's actually the case. If you compare the graph on the left and on the right, they are reflecting across the y-axis, right? Which are graphs of f and h. Okay, so that's reflecting, and we still have another operation with the or transformation of a function. That's called non-rigid transformations. What we have just done um, so far are called the rigid transformations. When you shift, you don't change the shape of the curve. You only change the location of the curve. When you reflect, you don't change the shape either. So those are called rigid transformations. But there is also something called non-rigid transformation that you do change the shape of the curve a little bit. Okay, so let's start from one example here. Uh, in this example, we need to compare the graph of each function with the graph of f equals square root, I mean the absolute value of x. So in part A, we have another function h equal to 3 times absolute x, and in part B, we got the function g equals 1/3 of absolute of x. Okay, so if you compare the original function f equals the absolute value of x, which is shown on the left, Okay, so that's the graph of absolute value of x. I think we talked about before. It's a V shape. Okay, the graph of absolute value of x is the V shape. Just to keep in mind. Now h equals 3 times absolute x, so that's just 3 times f, right? You multiply 3 to the function f, so you're going to get a high value for same x. Okay, so that means you're going to, you know, stretch the curve vertically up. Okay, so that's shown in the graph in the middle. Okay, so when you stretch the curve upward, you know, then obviously you are raising the value of y by 3, by a factor of 3. So the graph of h equals 3 times absolute x is a vertical stretch of f with a factor of 3. Okay, makes sense? On the other hand, in part B, we got g equals 1/3 times absolute x. So this time you multiply 1/3 from the original function f, which is absolute x, or divide by 3 in other words. So this time the value, the g value, function value for g is divided by 3, so it becomes smaller. So this time you need to compress the graph toward x-axis vertically. The curve becomes flatter, okay, because the y value decreases to the 1/3 of the original number, okay, or value. So the graph of g equal to 1/3 absolute x is a vertical compression or shrink of f to a factor of 1/3. You can see in the graph on the right side. Okay, so you do change the shape of the curve a little bit. All right. So from F to H, it becomes sharper, but from F to G, it becomes flatter. All right. So let's just combine those transformations and obtain, you know, different graphs of functions. So sometimes you you need to stretch or compress in different ways. So in the next example, we need to compare the graph of the functions of f with g and h, where f is x squared plus 3, and g equals f of 2x, and h equals f of 1/2 x. Okay, so g is f of 2x, so you are basically multiplying the variable x by a factor of 2. In this case, we're going to do the non-rigid horizontally. Okay, so again, this is not shifting, it's not reflecting, it's compression or stretching. Okay, so when you change x to 2x in f, you compress, you don't stretch. So this is contrary to the case of the previous example when we stretch or compress vertically. When you stretch or compress horizontally, the effect is the opposite. So when you change x to 2x in f, then you compress, you not stretch. Okay. So the graph of g equal to f of 2x, which is 4x squared. If you replace x by 2x, you get a 2x squared, which is 4x squared plus 3. At the end is a horizontal compression shrink of f to a factor of 2/2. So you squeeze it horizontally. In the part B, the graph of h equals f of 1/2 x. So this time you change x to 1/2 x in f. So you're going to get the 1/2 x to the square, which is 1/4 x squared, plus 3. And in this case, you stretch Okay, so remember this is opposite to the case of horizontal stretch or compression. So it's a horizontal stretch when you multiply half to x. It's a stretch of f with the factor of 2. Okay, so you're going to get the graph on the right side. You can see, and you need to change the shape of the curve a little bit, although they're all parabolas. When you squeeze, you get a sharper curve in the middle, and when you stretch, you get the flatter curve on the right. Okay, so these are the transformations of functions typically in functions graphs. Okay, any questions for this section? So if there's no more questions, then we're going to do another section today, 2.6. All right, so okay, we're going to talk about another thing in this section. You know, the whole chapter 2 is about functions and the graphs. Now we're going to talk about a combination of functions. In this section specifically, we're going to discuss composite functions. That means you can use the functions to make some other functions. All right. So let's start from arithmetic combinations of functions. That means you can add, subtract, multiply, divide two functions to get some other functions. So in the first example here, we got the function f equals x squared and g equal to 1 minus x. And then we can add those two functions together, the f plus g. And then we need to find the f plus g and the value that the sum when x equal to 2. So you just add those two functions. So f plus g is just the x squared plus 1 minus x, and the value of this sum of two functions at x equal to 2, which is written as f plus g and 2 is just 2 squared plus 1 minus 2. Just plug in 2 for x. For the whole thing, you get them 4 plus 1 minus 2, which is 3 if you do it. Okay. Similarly, you can also subtract two functions. In the next example, we get f equal to x plus 1, g equal to x squared plus 2x minus 1. So if you subtract the two functions, you get f minus g, which is 2x plus 1 minus x squared plus 2x minus 1. If you distribute the negative sign in the second part, you get 2x plus 1 minus x squared minus 2x plus 1. And you're going to cancel the 2x and get 2 if you add those two ones and subtract the x squared. And the f minus g at 2 is just 2 minus 2 squared. If you plug in 2 for x and the whole thing, you get 2 minus 4, which is negative 2. Okay, so that's pretty straightforward. You can do a similar thing with multiplication and division. So in this third example, we have two functions f equal to x squared and g equal to 1 minus x. We need to find f times g and evaluate the when x equals 3. So just do the same thing as we did before. This time we just multiply those two functions, x squared times 1 minus x. So if you distribute x squared, you get x squared minus x cubed. And then plug in 2 for x, you get the f times g at x equal to 2 equals 3 squared minus 3 cubed. Okay, so that's 9 minus 27, which is negative 18. So that's pretty easy. Now, in the next example, we're going to divide two functions, f and g. And then we need to find the domains of f over g and g over f. Okay. So f equal to square root of x and g equal to square root of 4 minus x squared. If you divide those two functions, you get the f over g, which is square root of x over square root of 4 minus x squared. Okay. Now, when we try to find a domain of this function, we need to consider several things. First, we need to find a domain of each function of f and g, and then take the intersection, those part in common for the domain of f and g. And then, in addition, we have another thing to consider. That's the denominator cannot be zero when you divide, two numbers or two functions. So we've got a few things to consider. So each of those functions is a squared function. So that will define domain of those functions. So since we cannot take square roots of negative numbers and the denominator of fraction cannot be zero, then we have x greater than or equal to 0 to be sure that when you take a square root on the top, it makes sense, right? When you take the excuse me, when you take the square root of x on the top, you're going to require x to be greater than or equal to 0, so that you're going to get a real number. Okay, so that's from the top of the f over g, and then at the bottom we got square root of 4 minus x squared. So again, you can only take square root of a positive number or 0, but since the denominator cannot be 0, so 4 minus x squared cannot be 0. So instead, it has to be greater than 0 strictly. So 4 minus x squared greater than 0. So that's why we got these two inequalities. For x greater than or equal to 0, we just leave as it is. And when you try to solve the inequality of 4 minus x squared, you're gonna get the x between negative 2 and 2. I think we talked about this before, inequalities. How to solve this inequality, 4 minus x squared greater than 0. If you solve it, you're gonna get the solution as x greater than negative 2 and less than 2. And then you need to take the intersection of these two sets. One set is x greater than or equal to 0, and the other set is x greater than negative 2 and less than 2. If you take the intersections, the part in common between those two sets, you're going to get x greater than or equal to 0 and less than 2. Okay, right? So that it makes sure that x is greater than or equal to 0 and also is greater than negative 2 and less than 2. Okay. So this problem is a little tricky. It involves quite a few steps. Okay. Similarly, when you divide g by f, so this time you just flip it. So you're gonna get the square root of 4 minus x squared over square root of x. Similarly, we have to consider each part. Okay, on the top, we will require 4 minus x squared greater than or equal to 0 to make sure when you take the square root of this, it makes sense. And in the denominator, we need to have x greater than 0 so that when you take a square root, it makes sense. And at the same time, it cannot be 0 because it's in the denominator. So in this case, we don't have equal in x greater than 0 in the denominator. Okay, and then again, x greater than 0 is just itself, and 4 minus x squared greater than or equal to 0. If you solve it, you're going to get x between negative 2 and 2, including both negative 2 and 2. So that's x greater than or equal to negative 2 and less than or equal to 2. And then you take the intersection of these two sets of x greater than 0 and x greater than or equal to negative 2 and less than or equal to 2. You're going to get the x greater than 0 and less than or equal to 2 if you do that to make sure x is greater than 0 and x is greater than or equal to negative 2 and less than or equal to 2. Okay, so this is the problem of finding domain of functions. Okay, and very important. Okay, and now we come to another topic. It's called composition of functions. So we talk about addition, subtraction, multiplication, and division of functions, but there's another operation of functions that's called the composition of functions. I mean, we use f circle g to denote this operation. It's defined f of gx. In other words, you replace x in f by gx. Okay, so let's just do one example and see how it works. Suppose we got a function f equal to 2x plus 5 and g equal to 4x equal to 4x squared plus 1. We need to find both f circle g and g circle f and evaluate f circle g at x equal to -1/2. Okay. So first f circle g by definition is just f of gx. So but gx is 4x squared plus 1. So that's just the f of 4x squared plus 1. So what I do is just replace x in f by 4x squared plus 1. So 2x becomes 2 times the 4x squared plus 1 when you replace x by 4x squared plus 1. And then you're going to add 5. So distribute the 2 in the first part, you get 8x squared plus 2, and then add 5. So at the end, it becomes x squared plus 7. So that's f circle g. You can do a similar thing now with g circle f. By definition, it's just equal to g of f. Okay. So be careful about the order. All right. The way to do it, it is similar, but the order is important. Okay. But f is just 2x plus 5, so g of f is just g of 2x plus 1. That means you're going to replace x in g by f, or 2x plus 1. So that gives you 4 times 2x squared, 2x plus 5 squared plus 1 when you replace x in g by 2x plus 5. And you need to simplify it. What you do, just 4 2x plus 5. And if you do that, you're going to get 4x squared plus 20x plus 25. You can easily double check it by either voiding it or using the formula we learned before. Okay. And then you distribute the 4 in the first part, you get 16x squared plus 80x plus 100 plus 11. So combine 111, you can get the 16x squared plus 80x plus 111. It's not 101, I'm sorry. So that's a typo here. So in the last part, we need to evaluate the f circle g at the x equal to -1/2. So what you do, you just plug in -1/2 for x in f circle g. So f circle g is just 8x squared plus 7. So plug in -1/2 for x, you get that 8 times -1/2 squared plus 7. -1/2 squared is 1/4. So you get 8 times 1/4 plus 7. 8 times 1/4 is just 2. 8 divided by 4 is 2, right? 2 plus 7 is 9. So that's the final answer for this part. So that's the composition of functions. Okay, so let's just continue with this topic for 2 more examples. In the third example, we have f equal to x squared minus 9 and g equal to square root of 9 minus x squared. Okay. Find the domain of f circle g. So we need to, find the domain of f circle g. We're not asked to find f circle g, but find the domain of f circle g. Okay. Again, just start from definition. F circle g is just the f of gx, which is f of square root of 9 minus x squared, because g is square root of 9 minus x squared. So first, we have to make sure, when you take a square root of 9 minus x squared, it makes sense. So that requires 9 minus x squared to be greater than or equal to 0. If you solve this inequality, you can get the x greater than or equal to -3 and s or equal to 3. So x between -3 and 3, including both -3 and 3 at the end. So the domain of this function f circle g is just x greater than -3 and less than or equal to 3. Okay. All right. So that's this example, and the last example is to write the function h equal to square root, cube root of 8 minus x over 5 as a composition of two functions. So we are doing the opposite this time. We are given a function and we try to break it into a composition of two functions, and there are different ways to do it. This answer is not unique. So for example, we can let f equal to x over 5. If you look at the whole structure of this function, it's a division, so you can let f equal to x over 5, and then g equals cube root of 8 minus x. Then if you compose f and g, you get f circle g equals f of gx, which is f of cube root of 8 minus x, because g is cube root of 8 minus x. So what you do, you just replace x by cube root of 8 minus x in f. So that becomes cube root of 8 minus x over 5, because f is x over 5. When you replace x by cube root of 8 minus x, you get a cube root of 8 minus x over 5, which is exactly what h is. So so we got f circle g is the same as h. So in that way, we decompose h as a composition of two functions, f and g, where f equals 1, x over 5, and g equals cube root of 8 minus x. So this question is just asking you to decompose a function to get f and g, asking you to tell what f and g are. Okay, but it's not the only way to do it. You can do it in another way. Okay, for this problem. So that's the end of this section. So we finish this section. As I said, I'm not going to go any new material now. So let me just stop the recording.